Hi, my name is Feiyang Zhu. I'm a fourth-year PhD student in CPIS, and my advisor is Dr. Qiang Li. I got my bachelor degree from Wuhan University in China. My research interests are high-frequency inductor design and integration for point-of-load converters. Today, I will talk about multi-phase coupled inductor analysis for voltage regulators.
The voltage regulator design becomes more and more challenging in smartphone application. Here shows the VR design in iPhone 8. On the front side of the motherboard is a microprocessor. On the back side is a PMIC together with other passive components. It can be seen that capacitor and inductors occupy lots of space. And one reason is that the switching frequency of today's PMIC product is below 5 MHz. And another reason is that it's quite challenging to shrink the inductor size. Therefore, advanced inductor structure is required. Then CPIS proposed this three-dimensional integrated voltage regulator for the smartphone. So the inductor is right beneath the microprocessor and stacked with a PMIC to provide a very short power delivery path. The switching frequency is pushed beyond 10 MHz, and the multi-phase integrated magnetics is required. And finally, the inductor will be embedded into the PCB like this. And the inductor can even embed into the motherboard to achieve even higher power density solution. To realize this, first we need to characterize the proper high frequency magnetic material. The second is we need to propose an advanced integrated inductor structure. Here shows the characterization of two high frequency PCB integration compatible magnetic material. One is metal flake composite from talking, as shown by the solid lines. Another one is the LTCC50, as shown by the dashed line. And in the interested design area, the talking material has lower color density. And here shows a permeability comparison. The talking material has higher permeability. Therefore, the talking material is chosen as the magnetic material for the inductor design. And here's the review of generation 1 design. First, they start with a single phase inductor. So the wire is used as the inductor winding, and this wire will go through the magnetic core. Then, for single phase inductors are merged into one single piece magnetic core and become a 4-phase inductor. From the flux distribution, it can be seen the middle area of the core is not fully utilized. Therefore, another phase is added in the middle area of the core and become a 5-phase integrated inductor. For this structure, it has several benefits. First, there's no air gap, so the outer flux is confined in the core, and it can achieve 5-phase integration with very low profile. And because the winding structure is very simple, so it has very low DC resistance, and it can support 50 ampere load current in total. However, there's an issue in this structure. If you look at the loss breakdown, the cut loss is much higher than the winding loss, which is not good. So the motivation of this structure is to reduce the cut loss and further shrink the inductor size. And here is the generation 2 design with the proposed inductor structure on the right-hand side. So it's a 4-phase integrated inductor structure, and the wire number for each phase is increased from 1 to 3 to reduce the cut loss. And for each 2-phase inductor, they are negatively coupled, so the DC flux in the core are reduced due to flux cancellation. And the additional benefit is that we can achieve large static inductance and small transient inductance at the same time due to negative coupling. And here shows the loss and size comparison. So it can be seen that the generation 2 design can achieve 50% loss reduction together with around 40% footprint and thickness reduction. And besides the new inductor structure, we also characterize the new magnetic material from 3M. So on the left-hand side is a color density comparison. The dashed line is the 3M material, and the solid line is a metal flake composite from the talking material, from talking. So it can be seen that the 3M material has around 60% color density reduction compared with the talking material. And on the right-hand side is a permeability comparison. However, the 3M has around 15 to 30 30 smaller permeability compared with the talking material. And here shows the inductor performance comparison using two different materials. The inductor dimension is kept the same for two cases. So the inductor structure with 3M material can achieve smaller core loss and total loss. However, the steady inductance also becomes smaller. So it's around 40% inductor loss reduction together with 20% smaller inductance for the inductor structure using the 3M material. Then we explore the possibility of embedding the proposed inductor structure into PCB. And here shows that the magnetic core is sandwiched into a two-layer PCB board. The top and bottom copper layer together with the vias are used for the inductor windings. And here is the detailed design parameters. So the magnetic core thickness is limited to 0.3 millimeters. So the total thickness of this PCB embedded inductor is as small as 0.6 millimeter. And here is one design example by using the talking material. So the total footprint of this four-phase PCB embedded inductor is 17 millimeters square with very small total loss. And here is the inductance measurement result of PCB embedded inductor. So the inductance are measured by using 3 different samples and compare with the simulation result. For each phase, the measured self-inductance and the mutual inductance can match well with the simulation result, which demonstrates the feasibility of PCB integration method with the proposed inductor structure to achieve high-density integration.
This is a simulation file of 8-phase buck converters with indirect coupled inductor. The inductors are built based on equivalent circuit model as shown here. This is a simulation waveform of current in coupled winding loop. These are the inductor currents. Based on the simulated steady-state inductance and the trending inductance value, we can verify the accuracy of the equivalent circuit model. To summarize, high power density voltage regulator design with fast trending speed is required for CPU and GPU applications. Compared with non-coupled inductors in multi-phase VR, negative coupled inductor can realize better circuit performance as well as smaller inductor size. However, traditional coupled inductor structure has a difficulty to achieve symmetrical coupling when phase number is larger than 2. Then, indirect coupled inductor structure was proposed. The detailed analysis of this structure with equivalent circuit model is performed in this paper. It is found indirect coupled inductor can achieve symmetrical coupling regardless of phase numbers and has very good circuit performance when phase number is large. Furthermore, another coupled inductor structure named as hybrid coupled inductor is analyzed in this paper. This structure can be seen as a combination of traditional coupled inductor and indirect coupled inductor. More detailed analysis of this structure will be done in the future. This work is supported by Power Management Consortium. Thank you for your attention.